Hi, this is a recording from class notes on March 7th or March 8th. It's Chapter 9, wrapping up confidence intervals and linking them with the two-sided test. First question, we have a pharmaceutical company claims that medicine will produce a desired effect for a mean time of 58.4 minutes. So since that's what they're claiming and that's what we're given as our mean, this is a mean, so we're talking about a t-test or a t-distribution. This has to be our mu, is 58.4. Government researcher runs a hypothesis test of 25 patients. So 25, that's our n. And calculates a mean of x bar equal to 59.5. That's your sample statistic with a standard deviation of s equal to 3. In the calculator, that's s sub x. He observes the data are roughly symmetric and unimodal. Roughly symmetric and unimodal is checks for us when we check our conditions. Compare the results of the two different scenarios below. So first one, we're looking to see, comparing our null, that the mu equals 58.4 to an alternative where it's greater than 58.4. We're going to assume that the parameter was already written out in context. We're going to come back to the picture part, but we're going to put in this information into our calculator and look at our t-score and our p-value and draw the picture for it. So, looking at my calculator, I have stat, I'm doing a test, and I want a t-test since I'm talking about means. I have statistics given to me in the problem. Mu sub 0, that's your HO. Mu O, H, O, 58.4. Your x bar in this case was 59.5, and the s sub x was 3. We have a sample size of 25, and I'm going to look at, when I pick the bottom part, it's exactly how it's written on my HA. It's pointing to the right, so I should select the one pointing to the right. Calculate. So here's all my information, and I'm going to copy it down onto my paper. So my t-score is 1.833. My p-value is 0.0396. And then there is a picture part up here. So I'm going to go back to the test, and instead of calculate, I'm going to draw. Stat, test, t-test, draw. Uh-oh, I have something going on in my y equals. And here comes my curve. Sorry, there's a glare right there. I'm going to first clear that out. And then, will my graph show? Nope. I have to go back to stat, test, and draw again. And I'm just going to copy that graph onto my paper, and I'm showing that the middle should be that 58.4. This line here represents my sample statistic, 59.5. When I did the t-score formula, I found that this t was 1.833. Well, technically, I didn't do the math, the calculator did. This little shaded area, otherwise known as our p-value, is equal to 0.0396. So the conclusion, remember they didn't give us an alpha level to compare it to, so we'll use the standard alpha equal to 0.05. If p is lower than 0.05, you reject your HO. So since the p-value equal to 0.0396 is lower than alpha equal to 0.05, you reject HO. You can also say that now you have evidence. There's evidence that the mean, what was this about again? Something. The mean time is greater than 58.4. So the whole point of this exercise is not to try to cram all this stuff into this little box, but to compare the difference between a one-sided test and a two-sided test and what happens with your p-value. So I'm going to go over here and not write as completely. If you'll notice, everything stays the same in the problem. The only thing that changes is the HA. The alternative hypothesis is now not equal to. This is called a two-sided test, otherwise known as a two-tailed test. Whereas before we were only pointing in one direction, so it was known as a one-sided test or a one-tailed test. If I go back to the calculator and hit stat, test, t-test, the only thing I'm changing here is that not equal to, calculate. Notice the p-value jumped. It's twice as big as it was before. It's 0.079. The t-score, however, is still 1.833. Now, if you're curious, let's look at the picture. If I go back to t-test, hit enter, and I'm going to draw. And even though our statistic pointed us in one direction, we're still having to compensate and shade both ends of the curve, since in the alternative we weren't clear as to which direction the statistic would put us in or lead us to. So for our picture, I'm shading both ends. Each of these little shaded parts makes up that 0.0396. The two-tailed test, or the two-sided, multiplies your p-value by 2. This t-score is the one that we ended up with, of 1.833. However, if we were to look at the other end, this would be a negative t-score of 1.833. So conclusion, now the combined p-value, 0.079, is larger than 0.05. So since p-value equal to 0.079 is greater than alpha equal to 0.05, we fail to reject HO, and you would say we don't or do not have evidence, and then you would restate the HA in context that the mean time is greater than 58.4. So the question below the chart asks, the significance test in the previous problem gives convincing evidence for a one-sided test but not for the two-sided test. Why? Well, for the two-sided test, the p-value was doubled, causing it to be greater than alpha equal to 0.05. If we look down at number 2, Two agronomists analyzed the same data, testing the same null hypothesis about the portion of tomato plants. By the way, an agronomist is a person who studies the soil and crops. And they were studying these tomato plants suffering from blight. One rejected the hypothesis, but the other did not. Assuming neither made a mistake in calculations, which of these possible explanations could account for this apparent discrepancy? Roman numeral 1 says one agronomist wrote a one-tailed alternative hypothesis, but the other used two tails. That is very possible. We just went through that example above. So yes, that is possible. That's exactly what we just experienced up here in this problem. Roman numeral 2 says they wrote identical hypotheses, but the one who rejected the null used a higher alpha level. The alpha level is your significance level. That's what you compare your p-value to. Remember, that can change. The standard one we use is 0.05, but it could be 0.10, it could be 0.01. If your alpha is less than let's write it in terms that make sense. If your p-value is less than alpha, that means you reject your HO. And if your p-value is greater than alpha, then you fail to reject. So, if the one who rejected used a higher alpha level, let's say 0.10 instead of 0.05, then they would be more likely to reject the null because their p-value didn't have to be as small. So yes, Roman numeral 2 is correct. Roman numeral 3 is the opposite of Roman numeral 2. They said they wrote identical hypotheses, but the one who rejected the null used a lower alpha level. That wouldn't make sense because that means your p-value would have to be even smaller, and why would you reject the null if your p-value was too small? So it's just 1 and 2, which means the answer is D. Now in the back. Number 3. At the Baltimore Crab Cake Company, managers are interested in the size of crabs they used from the Chesapeake Bay. Last year, the mean weight of the crabs they used was 12 ounces. So since they're giving us last year's information, that is your mu. Managers wonder how different the weights of the crabs are this year. 50 crabs are randomly selected to test. So we have 50. That's your sample size, n equals 50. The mean weight of the sample was 13.4. So 13.4, that's your x bar. Standard deviation was 4.349. That's your S sub x. Do these data provide convincing evidence that the mean weight of the crabs has changed this year? So we need to do your state, plan, do, conclude. State, you need to define your parameter. Mu, that's the mean. Since we're dealing with means, we're talking about averages, mean weight. We're not on proportions, we're on T. As soon as you see mean for some of you, write yourself a big T to remind yourself that you're doing T distribution, T test, or T interval. State, the mu is the mean weight of, now remember we need to talk about the whole population. So of all crabs in the bay. Also that goes with our state is the hypotheses. We need the HO. That's saying the mean, it should just stay the way it is, that nothing's ever going to change in the HO or whole land. So we just write it as 12. And the HA is that mu. What were they thinking? Oh yeah, they said they wondered how different they are. So not equal to 12. That's your state. Your plan. We need to check our assumptions and conditions. Remember the random? Did we have a random batch of crabs? It says that they were randomly selected to test. So yes, we have a random sample of 50 crabs. Now, normally if they gave us data, we would then make a graph to make sure that the crab weights are symmetric, unimodal, without outliers, but there's no data. Yeah, hi Mary. I'm recording the notes from section from yesterday and Monday. So, since 50 crabs is more than 30, we're good to go. So I'm going to put a comma, which is greater than 30. Remember, we have to say why we're checking these conditions. So I can say now it's okay to use the t-distribution and do a t-test. So this is the fun part. Jump to the calculator for the do. Stat test. T-test. I'll erase you. Stats 58. Oh, nope, it changed. 12, 13.4, 4.349, 50, and not equal to, so calculate. And there's all our information. So here our t-score is 2.276. Our p-value is 0.027. I could write more, but I've already highlighted in the problem, so I don't need to rewrite it. It's pretty much all I need right there. I could draw myself a pretty little picture. Remember, it's going to shade both ends, and each end would be approximately 0.01356, something like that. 0.01356 in the middle. And then to conclude. And remember, if P is low, what do? You reject HO. So, with a p-value equal to 0.027, which is lower than alpha equal to 0.05. If you can't write that alpha, it's not a big deal. Say significance level. I know some of you struggle with that. We reject HO. And then, more importantly, we have to say we have evidence for the HA. We have evidence that the mean weight of crabs differs from 12 ounces. Done. Okay, that was a nice little practice. Notice how I squeezed it all in a little section. Some of you write too big to do that. I understand that. You could use a separate piece of paper. But now we want to compare it with a 95% confidence interval. So we still have all our same information. We've already checked all the conditions. We don't need to do all that again. Go to your calculator, hit stat, go over to test, and I'm looking for t interval. Oops, there it is, number 8. I still have statistics, and hey look, it kept all that stuff in place for me. I didn't have to do anything. Calculate. Calculators are lovely. Here's our interval. 12.164 to 14.636. So, down here, we should say we are 95% confident that the true mean weight of crabs in the bay falls between 12.164 and 14.636 ounces. So C, how does your confidence interval support the answer you gave in Part A? Well, in Part A, we rejected our HO. We said that it wasn't equal to 12. Our confidence interval, does it include 12? Is 12 in there? Or is 12 way down here somewhere because this is 12.164? Okay, really, it's right next to that interval if we were to draw a number line, but the main thing is that 12 is not in this interval. So mu equal to 12 is not within the 95% confidence interval. If the interval did contain 12, we would have failed to reject the HO. When it's not in the interval, you have evidence to reject your HO, and when it is in the interval, you don't have evidence to reject HO. What does the confidence interval provide you with that the significance test did not? Well, remember we rejected the HO. We rejected the parameter that the mean was 12. So that means we have no idea what it is, but it provides us with a possible range of values that the true mean might fall in. So the interval provides us with a possible, it's okay, Quinn, range of values that the true mean might fall in. What confidence level should you use if the test had been one-sided? Well, we had that the alternative up above, we had that it was not equal to 12. And we were comparing it to alpha equal to 0.05. When you compare when it's two-sided and you compare your alpha to 0.05, that alpha level is kind of split between these two ends. You're still combining these two ends to that same alpha level. So for an alternative that's two-sided, meaning mu not equal to, compared to alpha equal to 0.05, your confidence interval has to have half of that 0.05 on either end, which means that 0.95 is in the middle, because on either end that 0.05 needs to be split, 0.025 and 0.025. However, when you use a one-sided test, so this was two-sided, one-sided test, let's just say that for the alternative we thought maybe that mu was greater than 12. We're still comparing it to 0.05. But we're only looking at one end of the curve being within that 0.05 range. Since it was greater than, I'll shade the upper end. This is 0.05. Well, what's cut off in the middle? I know we're only looking at one end, But in order to consider a confidence interval, we have to consider this end being knocked off over here too to make it symmetric. So the end we're not looking at is also 0.05, which leaves us with 0.90 in the middle. So for one-sided, it should have been a 90% confidence interval. Now, this stuff is really stretching your brains, I know. It's how they all connect. And there's more tests and intervals for us to go through, different types, but this is the groundwork for everything to come. That's what you missed in class on Monday and Tuesday.